gracias a todos por venir. Es un placer darle la bienvenida al profesor Vasily Leonenko de ICMO University en San Petersburgo, y pues nos va a platicar un poco sobre el trabajo que han hecho de modelado epidemiológico, y pues digamos estamos empezando una colaboración aprovechando los datos que ellos tienen con análisis que hemos desarrollado aquí en la UNAM, y pues bueno, por favor Vasily, platica.
Buenas tardes, estimados colegas, muchas gracias por venir, y creo que voy a hacer esa presentación en español, en inglés, aunque me gustaría hacerlo en español, pero me falta palabras a veces, así que cambiamos a inglés. So the topic of today's talk is modeling and prediction of influenza outbreaks in Russian cities, and I'm going to talk about my experience in the field, like what is the problem, why did we start to deal with this, and what results did we get. But also I've put some information about what we managed to do with Dr. Gershon-Sonaki here. And I will show some new information we got using techniques that Dr. Gershon showed me, and which he used in his own works about analyzing different types of data. So at first, several words about why do we need to forecast influenza at all. The thing is that although influenza is kind of widely known, and it doesn't, it's not so deadly, so to say, like tuberculosis or maybe HIV, still it has some bad implications for the health situation in the country. And particularly it causes a lot of burden on the healthcare system, and the disease complications such as heart diseases and strokes, they cause essential number of deaths every year. This we cannot deny as well. So if we can forecast how the influenza outbreak will look like in the consequent season, so what will be the incidence, like when will the peak of incidence occur, and that kind of things, so we can treat the oncoming influenza epidemics more effectively. The thing is that in Russia, in comparison to a lot of other countries in the world, we have a kind of broad database of influenza incidents, because influenza is officially a reported disease in Russia. So every healthcare unit has to report the numbers they get each week to the center. And thus, we have obtained a very big and interesting database of influenza incidences. That there is a good remark here I need to make. The thing is that in Russia, they collect the incidence of acute respiratory disease, or shortly ARI, which is not actually influenza, because it is very hard to distinguish influenza and acute respiratory disease if you do not do any laboratory studies. Usually in Europe, for instance, in WHO in general, they report something which is called influenza-like illness. It is the disease which seems to be acute respiratory disease. It has symptoms like fever, cough, and temperature like up to 39, 40 degrees. And this is the data they collect. In Russia, they collect every types of acute respiratory disease. That means if you just have a slight cough or problems with your nose, and you go to the doctor, he will report you like a case of ARI. So for us, it was also problematic to, and it was an important task to distinguish the incidence of ARI from influenza epidemic incidents, but I will talk about this a bit later. So here we got weekly incidents, that is the number of new cases each week in 49 cities of Russian Federation, starting from 1990 and up to this very moment, because they collect the information on a weekly basis, and Research Center of Influenza with whom I work. And also they divide the incidents into 4 age groups. So like small children, which is like toddlers, and preschool children, school children, and adults. And so this database can be handled to try to, as we try to use it to calibrate our forecasting models and do some influenza incidence forecasting. If we show this incidence on the graph, it will look like this. So basically, you can see that there is a very distinguished epidemic curve here, and it is preceded by the two different levels of seasonal acute respiratory infections. So in summer, usually this level is quite low, in winter it's a bit higher, autumn and winter. And then in some years we have this incidence outbreak, and in some years we don't have it. And here, for instance, you can see that there are two kind of waves, but the first one is not recognized by the healthcare specialists like an epidemic of influenza, and it just passes by, and then it is followed by another wave, which is considered to be a real epidemic. So the first problem when it comes to prediction of the dynamics of ARI is to distinguish like those phases and try to understand which of them are important for us and which are not. So we started with analyzing those incidences and comparing them to the, like matching them better to say to the values of specific humidity and temperature. The thing is that it is known that influenza could be caused by some external factors, but when it starts, usually it is generally defined by contacts between the people rather than by the external conditions. Whereas if we have ARI, like a simple cough, you can imagine that if it is summer, you don't have cough and fever usually, like this common cold, as they say. In autumn and winter, you can get it, but still, usually you don't get it from other people because it is not so contagious like flu. So we decided to try to distinguish ARI and influenza in terms of external conditions. And here you can see that if we return back on this slide, like everything which is not an influenza outbreak wave, we marked with blue here, with blue dots. And the thing which is an outbreak, we marked with red dots. And we plotted those dots, like it is basically an interpolated daily incidence. We plotted it against the specific humidity in this very day in this particular city. So you can see that those two clouds of plots, they are quite different by their nature. Here you can see the clear correlation between the specific humidity and the incidence. And this epidemic cloud, so to say, cloud of points, it doesn't depend too much on temperature and humidity. Here is the same graph temperature. So as we understood that there are clearly two different processes which constitute the ARI incidence, and one of them is attributed to common cold, and it could be explained by the changes in temperature and humidity. Whereas another one, which is here, it is an epidemic outbreak, and it is not so much defined by the temperature, except the fact that also there is clearly some kind of a barrier which it couldn't pass in humidity and in temperature. So you can imagine that if we have St. Petersburg and we have 10 degrees there, so it's highly unlikely that that epidemic outbreak will occur because the conditions are not favorable for this. But when we pass this barrier, so we have less than zero degrees, then the epidemic could happen. But it is not guaranteed that it will happen, but it could happen. So we decided to work only with the epidemic data. So like we did here, we basically extract the ARI levels attributed to seasonal conditions, and we work with the epidemic wave. Because here we can basically predict this ARI level statistically. It's not a very big deal. And a thing which is important for us is the outbreak. So now we switch to the modeling of this outbreak. And the question was what type of models to apply here. And it is not very clear because, for instance, now, well, it used to be 10 years ago like that, but now it's still on. I think the agent-based modeling is quite popular, and everybody is trying to do agent-based modeling in any case and include other factors to the model. Whereas sometimes maybe it is more efficient to use some simpler model, like Kermack-McKendrick model of 1927, which is very simple, could be tuned to any data, and it consists of a few parameters. So it is easier to work with it when the data is scarce. In our case, we have a broad source of data, but it only constitutes incidents. So we don't have too much information about the contact rates, which are here. And it's better to stick to the simpler models. So we started to look in this direction. And first of all, the thing is that in Soviet Union, there was a efficient and successful experience of modeling influenza spread throughout the country. And they basically use the type of model of Kermack-McKendrick as well. That type, only they converted it to the difference equations. And this model is even simpler because they have only like this, in addition to the parameter, which is the size of population here, rho, they have only two epidemic parameters. The first is beta, which is the contact rate. And actually, this is an efficient contact rate. So it's the rate of transmission of influenza virus via contacts with contaminated persons. And another one is the number of susceptible, like the ratio of susceptible persons in the population in the start of the epidemic. So if you calibrate the model, like if you find two values, alpha and beta, basically you've covered everything. So you have a calibrated model and you can use it for predictions. Also, they had global epidemic model, which basically is a local one, but multiplied by the number of, like, distributed for every city which they considered, because despite, like, in addition to the contamination which happens within the city, there is intercity infection transmission as well, which happens due to the migration of infected individuals. So basically, they just added here a component which is describing the flow of people throughout the country, like from city A to city B, and they received the global model out of the local one. So the idea was the following. Here we have three graphs. This thing is a bit sluggish, but I guess I will show it anyway. So you can see here one epidemic year and ARI incidence, which was demonstrated in this year. So basically, there are one small wave, another wave which is bigger, and the epidemic wave finally. And this is the data for St. Petersburg. So if you look at Moscow, for instance, you can see a very close, very similar picture. And if you look again at another city, at Novosibirsk, you still see the same picture, although the details are a bit different, but the idea is the same. And so the idea of Barayan and Arvachev, who were the authors of the model, is that in a given epidemic season, the incidence rate, like the incidence graph, will behave similarly in any Soviet city under consideration. And so imagine, for example, if we have one of those three cities which demonstrated the epidemic outbreak the first. For instance, in St. Petersburg, it started earlier, whereas in Moscow and in Novosibirsk, it didn't start. And if we have the picture of this outbreak in St. Petersburg, we can actually guess what will be the picture looking like in other cities, because it will be basically the same. The numbers will differ, but the overall idea is the same. So the thing is that when we have this very first outbreak in the country, which already reached its peak here, the maximum incidence, we can basically calibrate the model using this data. So acquiring the values of, here it's called lambda, but in the model it was beta. So it is alpha and beta. When we calibrate the model, we get alpha and beta, and then we have the transport model, which demonstrates all the transport connections in the country, which are assessed by the number of airline tickets and train tickets which are sold. And so imagine if we start an epidemic in St. Petersburg, we have a local model which is tuned to St. Petersburg. We know the parameters of this local model, and as well we know the parameters of the transport network. So we can calculate how many infected persons will migrate from St. Petersburg to every other city, and consequently we can understand how the epidemic will start in every other city as well. And then we can apply our local model, which is already calibrated. So basically, and with this method, when we have only one outbreak in one city in Soviet Union, we can predict all the other outbreaks, including their time, the moment of their start, I mean, and the time and the height of the maximum incidence of the peak. So that's how it worked. And actually, it worked quite well. But this model was used in 70s, and it was started in 1971, I guess. It was like applied first, and then they used it like for a decade. But in 80s, it started to show some growing incoherence with the real data. And sometimes the model, for instance, showed that there is a peak appeared in the city, like it predicted the peak and quite a big one. But in the real situation, like when we wait 2 or 3 weeks, we see that there is nothing happening there. So there is no epidemics. And it was kind of strange because earlier it worked almost flawlessly, but from the one moment it's just ceased to work. And the thing is that later, like in late 80s and then the 90s, there was an economic and political problem in Russia and Soviet Union. So basically, Soviet Union ceased to exist, and that's why this model wasn't elaborated further. And at this moment, we decided that maybe we can try to understand what happened with the prediction force of the model and try to make some modifications to make it work again. Not this maybe model, but just come to some, maybe we can just come to another model using the more contemporary and more prominent techniques which are available at the moment. And that was our aim. So basically, we had two things to look for. Like at first, we thought that maybe the transport data was unreliable and the local model works flawlessly, but the transport structure has changed, and that's why maybe they started to show some strange results which were not right. And another question to was maybe this is not the transport data, maybe this is a local model which is not adequate anymore. And we thought that maybe it could be connected with herd immunity. And actually, this is not my opinion. This is an opinion of one of the three people who worked in the forecasting of influenza in Soviet Union. He said that according to his assessment, now we have big levels of background immunity in the cities, which are different from the city to city. Like as you can see before, in this concept, they used one first city to predict alpha, which is the number of susceptible persons in the population, the ratio. And they basically thought that this ratio is the same throughout the country. But it looks like, whereas, for instance, the contact rate may be the same because it is mostly influenced by the influenza strain, which is circulating at the moment. So lambda may be the same, but alpha could be different because the levels of immunity are different. And so we decided that maybe this is the case, but before we decided to work with the transport data because it was a more simple solution than to try to dig in and understand what was going on with the herd immunity. So at first, what we have done is that we just throw away basically the transport model because we didn't have reliable data on transport connections at the moment. And we modified an algorithm which was used in the 70s, but to see whether it will work at the moment. So what we have done, we were doing the calibration in the same fashion like it was done in the 70s by the first outbreak data. But then instead of relying on transport model for the prediction of the moment of epidemic outbreak in other cities, we decided just to wait until the epidemic really starts, and that by that we will know when it is actually. we won't need to predict its start because we will have it, and when it starts, we can try to apply this old technique of just like drawing the curve, which already we've seen in another city, to applying this to this city, and like to try to show if this old curve will predict us the real curve of incidence in new cities under epidemic. And so that's how it goes. We had some retrospective data. The points in blue here are the data which we were trying to predict. So we can imagine like we were getting another epidemic curves from another cities. Here it is St. Petersburg and Novosibirsk. And we were just waiting until the epidemic will start in Moscow. And then we simply cut and paste, I can say, all the epidemic curve to this moment, adjusting by this day of the outbreak. And then we see, does it predict our peak here? Well, I wouldn't say it predicts it so well. So it kind of gives you the overall idea, but not very good, not very well, not very corrected. And here we were trying to collect all the data we had and to assess the quality of predictions we achieved. So here we used the three criteria which were used earlier by the Soviet authors and researchers. Basically, we have three of them depicted here. Like one of them is called horizontal stripe. It means that like every point of prediction, I need to say what is the X and Y here. X is the peak moment prediction bias. So for instance, if you have an ideal prediction, it will be here because you don't have any bias. It's like the difference between the real data and your prediction is zero. So you have your point here. And on Y, we have peak height ratio. So it is the ratio between the maximum incidence which we predicted and the maximum incidence which we had in real time, in real life. So the ideal prediction will be placed in 0, 1. So we have zero bias in predicting the day and one ratio between the peak heights. So it's like the peak height is predicted flawlessly in this case. But as you can see here, like horizontal stripe shows how many points fall within the prediction, which shows you like from minus 20% to plus 50% of the peak height. So it's like plus minus something. And the vertical stripe gives you the number of points which predicted well the day of maximum incidence. So it's here it's plus minus a week. And the square combines those two parameters. So your prediction, if it fits into the square, it means that it will have considerably good prediction of peak height and the peak day. And whereas in the Soviet case, this gray points we have taken from the studies of 70s, they were almost inside the square. You see this, there is one which is not. But our predictions were worse. And whereas in the prediction of peak height, we were like more or less even with the Soviet standards, but the peak day was predicted awfully. You can see sometimes it gives you like plus minus 40 days, which is completely insane. It doesn't give you any information when you have this sort of bias. And so we decided to try another approach, which is even simpler than the first one we tried. Basically, we decided that we can take the incomplete incidence data and calibrate the local model on this data and like try to understand whether it will show us peak or not. So it looks like that. Imagine that you have an epidemic in St. Petersburg. So it started to demonstrate the growing number of incidence cases every week, every day in this case. And the blue dots are the dots which we already have, whereas the white dots, it is the real data which we don't know yet, and we need to calibrate our model using just blue dots because we don't have more information. And here we try to do this, to draw the incidence curve of the model through those data points we have. And as you can see, we kind of predicted the day of prediction here, more or less. Oh, sorry, the day of incidence peak, I mean. But the height is overestimated very greatly. So it doesn't feel like good prediction in terms of height. And then when we calculated the forecast accuracy for this type of prediction, we understood that the prediction of peak height was actually high, but it was high also in the previous case. And whereas the prediction of peak day was also not very good, it was just better than this previous approach with a local model. It was starting to get better, like when you have the data up to -4 days to the moment of the peak. So basically, they say that you can predict the peak day like in 4 days before it actually starts. So it's not a good thing. Like 4 days, it doesn't give you too much time to prepare the facilities and all that stuff. So when we understood that those simple things are not working, we came to the idea that there's not the transport model to be blamed, but rather something has changed in the process of the local distribution of the virus in the city, in the urban population. And we decided to dig in and to maybe to alter the model and to understand what we need to change to be able to accurately reproduce the actual influenza dynamics in the cities. So as I said before, our key was the differences in background or in herd immunities in the cities. So which is the average percent of the immune, which we can still capture using the differential model because we have alpha. Alpha is the percent of the immune. And another thing is that sometimes the immune are distributed unevenly. So basically, if you have dealt with differential equations of infection propagation, you know that they imply the homogeneous distribution of infected and susceptible individuals. That means that the contacts are also homogeneous, and essentially every person has an equal probability of contacting every other person in the population. Clearly, in small populations, it could be true if you have a small concentrated population. I don't know, like in a bus, for instance. But when we talk about cities, it's clear that, for instance, if you live in, I don't know, in Coyoacan, and there is somebody who is living east of Benito Juarez, clearly, if you don't work there, you cannot contact him because he will stay in his own area, you will stay in yours, and there is zero probability you will go there. So we had to consider this thing. And when this heterogeneous distribution of people takes place, so it affects greatly the distribution of affected cases as well. I have an example to show what do I mean by this. For instance, imagine that there are two cities. One of them is very connected, so everybody is very close to anybody else, and they contact a lot. For instance, a good case is sometimes the cities with subway systems. Although it's not entirely true, but subway systems, they increase greatly the number of contacts between people, because when you use, for instance, one line of subway, you can meet every person from every district there sometimes when you commute. So here we have a connected city, and another example is the clustered city. So the city where the individuals are staying at separate places and they do not contact outside of their groups. And imagine now that we have introduced the infected person in both of the cities. And we, as you might recall from the model of Parayan and Rachov, they assumed that those cities behave the same in case of epidemics. So that's why we can use the same curves to reproduce this epidemics when we know how it goes in the first city. Here, clearly, when we have a lot of contacts, this red guy will infect everybody, and we will have a big epidemic. And here, I think you can also have an idea what will understand or what will succeed. So here we have a small epidemic because this red guy cannot contact another cluster as he just stays in the cluster as where he appeared. And but the most interesting part is that what will happen next. Here, after people got infected, they got their immunity, and if the strain hasn't changed dramatically, they will stay immune or at least partially immune until the next influenza season. And when we reintroduce another infected person to those two cities, so there could be two options. And the city one, there is no options basically because everybody is immune and just there is no epidemic. In the city two, if this infected guy will appear in the same cluster, it will be the same thing as in the city one. There is no epidemic because in the cluster, everybody is immune and they don't have contacts with any other clusters. But if by chance you will go to another cluster, so we have a pool of susceptible people still here, and it will cause a small outbreak in the city too. So as you can now understand, if we have the same influenza strain introduced by an infected person in those two cities, in the first city, we will see a big epidemic outbreak with a high peak, and then we have nothing at the next year, next season. In city two, it will be like two subsequent small peaks. And this is totally motivated by the topology of the contact networks in both cities. So if we don't have this data about the contact structure, we will not be able to predict anything, basically. Or we can predict something, but it will be not very correct. And so we decided to try to deal with this thing, and actually this is what we are doing at the moment. So how to account for city-related differences? At first, we need a model which is more detailed than the differential equation one. And at second, we need to do a thorough incidence data analysis to try to preliminarily distinguish the cities by their contact structures and by the nature of the epidemics which occur there. So the first thing we did last year, I had a Fulbright grant and I was in the United States for a while. And with my supervisor from there, we were trying to apply the techniques from this institution, RTI International, to our problem. And the technique is called synthetic population. So basically, you create a population which represents a real one, but doesn't have any personal data, because you cannot just take a census, for instance, like the database of people living in some place and use it for your own purposes, because it will eventually bring you to the problem of data. And here is the representation, which is statistically correct, but still you cannot attribute a person to this database line, database row. And so you can use this population as a real one, but you will not have problems with privacy. In this synthetic population, we have people. It's like the list of everybody who lives in the neighborhood and the region which we are putting under consideration. We have households. Those are the places where people live. We have their workplaces. And also we have schools, because it's like in terms of workplaces for small people, for small children. So children like of school age, they go to schools instead of workplaces. This data we use to understand what is the commute pattern of people every day, so who can contact whom. And basically with this, we can try to understand how the contact pattern looks like, whether it looks more like city one or like city two, if we have this data. To deal with the synthetic population, I mean to try to launch the infectious, the process of infection in this population, we need an agent-based model. And at first, we used the open source framework, which is called FRED. It is available on the site of the Pittsburgh University, who are the authors of the model. And so if you want, you can check it out. It is available like an applet as well. You can launch some epidemics there in the American data. But also we eventually have come to our own framework, which depicts the same things which was implemented in the thread, but we know it better how to change it and how to tune it to our conditions, which are a bit different from the American ones. And the results were processed using the QGIS software and Python. And so here it is an example of how the epidemic goes. It is the map of St. Petersburg, and the green dots are the households which are susceptible, and the red ones are infected. So as you can see here, now we can understand how the epidemic spreads and what is the distribution of infected people. Like we don't just handle the number of them. We know where everybody from infected lives and who will he contact at the next stage. So that gives us more detailed explanation of what is going on during the infection. And for reconstructing the synthetic population in St. Petersburg, we used some Python scripts and some data which was acquired from the Russian officials, particularly the list of schools, the assessment of workplaces by their number of people who work there, their distribution, and so on. And we started from simulating the epidemics, which we already simulated using our simple model. So here you have the picture of the calibration of Barayan-Arbachev model, which I showed before. And here we have the threat simulation on the same data. And it was quite close to the data. Also considering the method we calibrated the model, it was quite simple. So we were actually very surprised to see the good result. And we were happy about this. And later we decided to play with workplace distribution. So to basically to change the topologies of the contacts of people and to see how it will influence the view, like the picture of the incidence curve. So here, the blue one, it is the real data. It is the actual real incident. And the three in other curves, they show the different incidence curves, which are caused by three different types of distribution of workplaces. So as we were talking about earlier, if you go to the center, for instance, every day to work and then you return, you have more probability to meet people in the public transport and to contaminate them or to get infected yourself. In comparison, if, for instance, you live at Kopilko and you go to work in Ciudad Universitaria, you don't need to commute at all. Maybe you can walk and you don't meet too many people in transport. And also you won't meet too many people from other areas of the city unless you go to some crowded university lecturing halls, and you will see a lot of students there, which would be also true. So here we have three distributions of workplaces. Like at first, our people of the population were choosing the closest workplaces to work in, and they didn't commute too much. Another one was just arbitrary set workplaces in 15 kilometers. So it is, if it is less than 15 kilometers, it is okay for you to work there, to commute every day. And for school children, it was schools in the range of 5 kilometers. And the third one was taken actually from the literature we had on the topic. So it is more close to real data as we think. 30 kilometers for workplaces and 1.5 kilometers for schools. And as a result, we see that the more plausible picture here was the third one. So I would say that the calibration procedures here were also very simple, so it doesn't coincide too much with the real data, which is blue graph. But at least it represents more or less maximum of incidents and the day of this maximum incidents. Whereas the two other curves, they show more even this more uniform distribution of the incidence cases during the outbreak. So it's not like that high peaked as this blue and black curves. And that brings us to the idea that maybe in some cities we have those situations with close workplaces and they have more evenly distributed infections, whereas In other cities, we have peaks, and clearly that will cause the different dynamics of the herd immunity forming in the cities, and that will cause also the incapability. Like, we cannot compare those cities when we try to forecast the epidemics. So basically, we need to understand what cities are like this and what cities are like this, and to distribute them in different categories and work with them separately, maybe. And this brings us to the problem we were dealing with Professor Gershonsona here. And we try to understand like what are the properties of cities in Russia as to their incidents and during the year, like a sum of incidents, and as to their peaks, the height of their peaks. So here in the map, you can see the distribution of the average cumulative incidence in the cities based on the data we have. And another picture, it is intensity, which is calculated like the opposite of Shannon's entropy on the same incident. So the idea is that in this map, we measure the sums. So for instance, here we have big sum of number of infected, clearly. But on the another map, we measure the unevenness of distribution of the incidence. So the higher is the peak, the bigger is the intensity. For instance, if we go back here, in this case, this green graph will demonstrate the highest sum, I guess. Well, not clearly. Maybe the black one will demonstrate the highest incidence in sum. But if we consider the unevenness of distribution of incidence, clearly the black graph over those three will win. So it will have the highest incidence and the lowest entropy. And here you can see that those two things are not matching actually each other. For instance, the good example is those two cities, Ulan-Ude and Chita, which have very low cumulative incidence during the year compared to another ones, to another cities. But they have extremely high intensity. So it means that they are peaking each time. So whereas, for instance, if we take, what cities we can take? Syktyvkar, for instance, here they have like a big cumulative incidence, but like average intensity. So the peak will be not that sharp, but a lot of people will get infected, but not at this very moment. So they will be distributed throughout the year. And to try to understand what is the difference and what is the connection and how to clusterize those cities in terms of intensity and the cumulative sum, we applied the technique which was used in a lot of papers of Dr. Gershenson before. It is the technique of calculating the ranks. And the idea of ranks, it lies within the idea is that we can calculate for every year the top 5, top 10, top 20 cities with the biggest sum of incidents. And then we can rank them. So if we have a city with a rank 1 in the year 1990, like here, it means that this city, which is Nizhny Novgorod, it demonstrates the highest number of infected people throughout the epidemic season. And so we have later the city number 2, city number 3, and so on. So we just order them from the highest sum to lowest. And then we see what will happen with those cities throughout another years. So our idea was to understand if we have a city which ranked 1, so it has the highest sum, will it remain his position in this rank? So will it demonstrate the highest sum through all the years? Or it was just a coincidence, and in this year it was ranking 1, and another year it could rank like 30. So it will change dramatically its ranking throughout other cities in Russia. And as we see, mostly the cities with big ranks and the cities with low ranks, they maintain their rank throughout the years. So you can see Nizhny Novgorod here, it kind of maintains his highest rank, although sometimes it falls a bit, like has a rank 6, I think, here. And sometimes there are also new cities which, for instance, ranked 15 at first, but then they started to be ranked 1. And at the same time, if we look at the low ranks, the picture is close to this. We have some kind of a constant maintaining of rank throughout the years. With this exception, actually, I thought that it could be a flaw in the data, but I rechecked it several times, and it's not a flaw. It really happened like that. So it was ranked like 35, consistently 35, 30, and then it's suddenly started to be like 6, and then it returned to the initial situation. And as we discussed with